Hi, welcome to Fiber Focus, the podcast brought to you by Sumitomo Electric Lightwave, where we explore the world of fiber optic networks and all things connectivity. And today we are here with Dwayne Holst, who is a data center optical communications researcher for Sumitomo Electric Lightwave. And welcome to the podcast.
Thank you so much.
So happy to have you here today. Would you start off by telling us a little bit about yourself? I understand you have an interesting background. You've been in the industry a while.
Yes, I have. Basically, this all started about 1984, so it's been a long time. And it has been a journey. I've watched a lot of technological breakthroughs, the way we communicate evolve completely. And along those same lines, I've never seen anything like what's happened in the last year and a half. Artificial intelligence is changing not only everything we do as human beings, but it's changing everything you don't see. The entire infrastructure, how it's built, how it's envisioned, what do we do going forward. I'm seeing the same sort of situation we faced in the late 80s, early 90s, designing silicon devices, where prior to that, we could design interconnections between devices, transistors, and whatever else by hand. You could just sit there and connect them. Once it became where microprocessors started being designed and there was millions of connections, now we could no longer do that. So we had to move into software arena to do things like engineering design automation, where automatically computers would design these chips and do all the millions of connections for us. And then we stepped up to just doing verification and verifying that the design met our specs. I'm seeing the same thing happening now in the physical layer for data centers and the interconnection networks.
Engineering, design, automation. Can you explain that for anybody who doesn't understand?
Sure. So basically, it's a large global macro description for basically an aggregation of tools that are used to do something very complex. So basically with silicon, it was, okay, we have to design the system. Now that we've got all these things drawn out, how do we simulate it? So we had to develop simulators to be able to actually run these things like they actually existed. Before you even do anything, you have a working simulation, and then you've got a baseline to where you could start a design. And then once you have that, then you take those designs and move them into what's called a physical layout, where you actually create the masks that are designed to build the wafers themselves, where you have many, many, many die. So many little instances of these chips. Same thing is happening, what is starting to happen with large scale networks. Data center interconnections is millions of connections are now becoming very difficult to do by hand. We're going to start to need the same sort of data automation that we did in silicon, where a computer and artificial intelligence using constraints can actually automatically generate what I call the next generation of digital twinning. Right now, digital twinning involves more of operation of data centers and simulating the data center to do what if exercises. What I'm working on is the concept of digital twin prior to anything being built or bought at all. So you can actually envision a data center or a digital network in complete virtual terms. So you can simulate it, you can optimize it before you order a single part. And then that design, much like layout in silicon, gets instantiated into an actual physical view of all the racks and GPUs and cooling and power. And then you can generate hyperaccurate bills of material. So you're not just buying a huge amount of stock and pulling as needed. You can actually have a bill of material that is right by design. And then it's more of a concept, EDA extends it all so that you also have the ability to, once you have the physical infrastructure built out digitally, you purchase the equipment, comes into inventory through whether it's through the operator or contractors, and then the system would output construction work orders for the construction. As these get checked off, they automatically check back into the database, flagging constructed, and the database or the application layer would generate testing instructions for the verifying teams to test. They check back in showing as tested good. Now you've got dark fiber that's ready to turn on. Then you go to the next step, which would be the whole DCIM or digital twin on the operations side, showing, okay, the data center is operating. Is it meeting constraints? Hey, did we hit simulation? No, the models need tweaking. So then you, through generations, you start to re-inform the models that AI would use to do initial design are getting better and better because we've got real communication between the logical design and the physical implementation and operation.
So is it a way of visualizing the data center? Is it like an advanced planning
Exactly.
system?
There are huge drivers of this. AI has basically caused a new growth in the infrastructure layer. Up until AI, we were very much human interaction, maybe some Internet of Things behavior was driving the growth of networking, following kind of Moore's law, maybe a little more accelerated. But with the explosion of AI and machines talking to machines, GPUs talking to each other, talking to the edge, all these things have caused an explosion. It's exponential growth on the data demands. The data's starting to require much higher specifications on signal integrity and noise and latency. The signals have to get there quick. The data has to transfer quickly. For all the applications, self-driving cars, drones, you name it, require instant processing of data and feedback. Because of this, these networks are growing massively. How do we design them? How do we deploy them in time, under cost, not only for the materials, but how do we save on the amount of power that's being required? We're seeing headlines every day that the grid is overwhelmed.
Yeah, so you're collaborating with, I would imagine, primarily hyperscalers and active equipment manufacturers, or what does your network look like in the work that you do as a researcher?
Right. So the biggest area where I'm focused on is I am kind of envisioning the demand that's coming and more of beyond just the specific use cases, whether it's hyperscalers or co-location providers or telecom, or it's more of as a technology, it's a massive amount of data increase, massive amounts of interconnections. How do we remove human error factors? Because as these things exponentially grow, human interfaces, human links within the chain provide an exponential growth in errors, which can cause massive overruns in cost, delay in time. So you want to try to automate this as much as possible and lift the human interface up to the next layer, which is more of a verification of automated processes.
Oh, very interesting. So it's using technology to help simulate the technology roadmap?
Yes.
Is that?
That's a great word to use, roadmap, because we can't build all of this at once. Much like it was done in silicon, this is going to be done in stages. What is the most urgent? Right now, possibly the most urgent, the way I'm viewing it, is the ability to simulate and optimize something before you even build it, so that you don't have a wasted amount of resources being thrown at something because you don't know exactly what it is you're working on. But if you can do the simulations and optimizations in a virtual domain, you can come up with a more efficient way of using, whether it's co-packaged optics or pluggable routes. It's to really nail down exactly what you're doing. So you save on cost on deployment, you order the right things, you know that the technology is going to do what you want it to do, and you can leave your space to scale, whether it's scale out or scale up. So I think that's the first step. The next roadmap would be obviously continuing that interface between simulation to construction to verification to operation, and then those all cyclically feed each other, helping the models, and everything gets tightened up and constraints can be more accurate.
All right, so it's not just like breaking it up into phases for the planning and the execution purposes, but also to get the feedback and kind of test.
You nailed it.
Okay.
The feedback is what's crucial here. I mean, there's already tools that do these individual tasks, but that's the key term here, tools, plural. When you have a wide array of tools, then there's a problem in the fact that you have to be able to do, okay, how do I get the data from that tool into this other tool? Okay, I'm going to have to do some sort of export, import, or manual data transcription or something like that. That is a bottleneck. What I'm envisioning is the same thing that happened in EDA, which is everything gets automated, everything's built on a single database, an object-oriented database where these objects, whether they're virtual or now they've driven an actual physical implementation, are all managed. And you can have automatic in and out behavior without having to do import, export, transcribe, aggregate. It's all done seamlessly, especially with the easy aggregation of AI bots that can be used on the front end. Some specific agents that will be used to guide all this behavior.
Okay, Dwayne, I feel like we could talk endlessly about this. I have so many more questions, but we are out of time. And for any of our especially smart audience members who want to dive into this with you, is there further reading? Are there any resources, or do they just need to get in touch with you directly?
I'm always grateful to hear from people who are actually in the field or who are having these problems to help me guide what I'm envisioning as a roadmap. And what are the priorities? Where are the pain points? What do we have to solve first? Because ultimately that's how investment has to happen, is where do we go first? And then as we solve a hurdle, what's the next hurdle? But I'm always willing to accept questions for further reading. I would basically just aim people at what happened with the development of EDA and silicon, because it's basically very similar problem. It's interconnections of large amounts of devices.
It's kind of where theory actually, what's the word I'm looking for? It's like we're taking it beyond. There it is. There it is. All right. Well, we need to hit the road. Dwayne, thank you again for being here. And thank you for joining us for this episode of Fiber Focus. Please share this episode with your colleagues if you found it helpful, and subscribe and come join us again next time.